So in this video, we're going to look at how to use bond energies to estimate the heat of a reaction. So first, let's go ahead and define bond energies. So let's look at a couple of different bonds. Let's just start with just some carbon-carbon bonds. Double bond, a triple bond, a single bond. And we're not going to draw the rest of the molecule, just the bond. And we're going to look at what the bond energy is. And we're going to say, let's look at this in kilojoules per mole. Okay, and for these different bonds, we can see they're different numbers. What do these numbers mean? This is the energy needed to break a bond. And I wanted to spend a few seconds on this because this is one of the more prevalent misconceptions, is that people think that energy is released when you break a bond. That's never true. It always costs energy to break a bond. And it is true that in some chemical reactions energy is released, but that means that in that reaction some bonds are made. In most chemical reactions, some bonds are made, some are broken. You pay an energy cost to break bonds, you get energy released when you make bonds, and the net effect, depending on whether you make bonds that are stronger or weaker, is that either the overall reaction releases energy or absorbs energy. So anyway, let's underline this just to belabor that point. Okay, so it costs energy to snap one of these bonds. And notice something. The more electrons you share between a given set of atoms, the stronger the bond. So it costs more energy to break a double bond than a single bond, and a triple bond than a double bond. It takes more energy. It's not linear. You can't say that this is going to be triple that. It's not, but it is more. Okay, so for a given set of atoms, bonds get stronger. They also get shorter as you go from single to double to triple. Okay, so if we can figure out the cost to break a bond, then if you make a bond, instead of costing energy, it's released. So by taking the difference between bonds made and bonds broken, we can estimate the energy given off by that reaction or absorbed by the reaction. Note, in this video, we're going to use energy and heat interchangeably. There's actually a subtle difference, but at the general chemistry level, we normally just ignore that. So if you're interested in that, you should take a thermodynamics course. Okay, let's do a calculation. We should define the heat of reaction. So the heat of reaction, so this is delta H, as if we're going to pronounce this. So it's delta symbol, and this is a R, so it just stands for reaction. So the change in this thing called enthalpy when a reaction occurs. And you can just refer to this as delta H, or the heat of reaction. That's perfectly fine at the general chemistry level. And what does that mean? Well, if delta H is a negative number, it means heat's given off. So think of an example like combustion. So if you burn something, clearly heat's given off, right? So if you think combustion, that'll be a good example of a reaction with a negative delta H, and we call these reactions exothermic. So if you have a negative delta H, we call it exothermic, exo meaning out of, so heat is coming out of the reaction, it's being released. And if you have a reaction with a positive delta H, heat is absorbed by the reaction. And we call that endothermic. So the reaction actually requires heat. Heat has to go into it. Okay, so those are our two cases, exothermic and endothermic. And in general chemistry books, you will sometimes see this written like this, RXN. This isn't really a standard way of writing it, but you might see it in a book, so I might as well write it. But the standard way of writing it is the way I've shown you here. Okay. Let's go ahead and see if we can estimate delta H for a particular reaction using bond enthalpies. So to do a problem like this, we should start by making a list of all the bonds that we break and all the bonds we make, because we're going to use this equation. And I'll write it two different ways. You can say that delta H is going to be equal to the sum of the energy of the bonds broken minus the bonds that are made. Okay, and this is just a summation. It just means you add it up. Okay, so it's just the total of the bonds that you break minus the total of the energy for the bonds that you make. The reason this term is positive is because it costs us energy to break bonds. This is negative here because we get energy back when we make bonds. Okay, so we broke this bond, broke this bond, we broke this triple bond, we broke this, and we better put a little line here to remind ourselves that we broke two of those. And over here, we've got and then we made some bonds on the product side. Right? We made this, 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 we made this. You can't forget the carbon-carbon bond in the middle. All right, so let's write all those down. So we've got two carbon-hydrogen bonds that we broke, and one carbon-carbon triple bond. And the bonds we made, oops, I skipped some of the bonds. We also broke two hydrogen-chlorine bonds. Okay, what did we make? So we made, looks like 1, 2, 3, 4 carbon-hydrogen bonds, and we made one carbon-carbon bond. This one's a single bond, and we made two carbon-chlorine bonds. Okay, so we can see we're going to add up all these energies. We're going to get from a table. You can find a table of bond energies in your textbook if you just search your book, either using a PDF searching tool or the index if it's a paper book, and you'll see there's a table of bond energies or bond enthalpies somewhere in your textbook. You can also look online, of course. I'd like to recommend a little time-saving trick, and that is to cancel things that are the same on both sides. So you'll notice we have these carbon-hydrogen bonds here, and they're still here on this side, right? So we have two here, we have the original two, we just added some. So what you can do is kind of like algebra. You can take the same thing off of both sides if you want to. You don't have to do this, but it will save you time. You can say, look, I've got two carbon-hydrogen bonds here, and I can get rid of two on this side too. And now that's one fewer number I have to plug into my calculator. Okay, but there's nothing else I can cancel because all the other bonds are different on the make and break side. So let's go ahead and do this problem. So we're going to have to write out the reaction. So we said delta H, and I'll write it out in full since it's the first one you've seen. We said it's equal to the energies of the bonds broken minus the bonds made. So first let's just write it as bonds. So we said we're going to have a carbon-carbon triple bond. We're going to have to break two hydrogen-chlorine bonds. So we have to add those up. And then we subtract the energies of the bonds that we make because that's going to release energy. So we said 2 times the bond energy of, oops, there's an extra line here. 2 times the bond energy for carbon and hydrogen. We're making 2 net carbon-hydrogen bonds. We have the energy for a carbon-carbon single bond, and we make 2 carbon-chlorine bonds. Okay, so now we're going to put in the actual bond energies, and for these we actually have to look at a table of bond energies. So we can see that we've got a triple bond, that's 837 kilojoules per mole. We've got 2 hydrogen-chlorine bonds, each of those takes 432 kilojoules per mole, and we've got 2 of those bonds we have to break. So this is the cost. This is the energy absorbed in breaking bonds. We get a benefit because we're making bonds too. So we're making 2 carbon-hydrogen bonds. We get this. So 415 per carbon-hydrogen bond, 345 for each carbon-carbon single bond, and there's 1 of those. And finally, we made 2 carbon-chlorine bonds, and so we have this energy released per bond that we make, and there's 2 of them. So all of this is the energy release. This is the benefit, this is the cost. Remember, this was the net number of carbon-hydrogen bonds that we made, because we made 4, but we broke 2, so I just changed it to the net. So if that's confusing, don't do that. Just don't cancel, just leave it. But you'll have to add 1 more number. All right, when we put all those numbers in, we end up with a negative 134 kilojoules per mole. So this is the amount, because there's a negative number, this is exothermic reaction. Heat's released when we do this because we made stronger bonds than the ones that we broke. And that's how you use bond enthalpies to estimate a heat of reaction.